Welcome to the Midnight Lesson. Tonight's lecture explores one of the most powerful forces ever to shape the North American continent. Not fire, not earthquakes, not even plate tectonics alone, but ice, vast, slow-moving and relentless ice. When most people hear the phrase Ice Age, they imagine woolly mammoths, frozen wastelands, and humans huddled around fires at the edge of glaciers. While those images are not wrong, they barely scratched the surface of what actually happened. Over the past several million years, enormous ice sheets advanced and retreated across North America multiple times. They scraped away mountains, rerouted rivers, created thousands of lakes, altered climate systems, and left behind the soils that now support forests, farms, and cities. Much of the landscape we take for granted today exists because of ice. The Great Lakes, Long Island, Cape Cod, the rolling hills of the Midwest, the fjords of Alaska. Even the course of major rivers like the Missouri and the Ohio were shaped, diverted, or blocked by glaciers. This lecture focuses primarily on the most recent glacial period, known as the Pleistocene epoch, and especially the last glacial maximum, when ice sheets reached their greatest extent roughly 20,000 years ago. But to understand that moment, we must begin earlier. We must understand what an ice age actually is, why ice advances and retreats, and how Earth's climate system allows glaciers to dominate entire continents. Tonight's lesson is not about catastrophe in the dramatic sense. It is about slow, patient forces acting over tens of thousands of years. It is about how ice moves, how it reshapes land, and how its legacy still governs North America today. We begin with the basics. Chapter 1. What is an ice age? To understand the ice age that shaped North America, we must first define what scientists mean by the term ice age, because it does not mean what most people assume. An ice age is not a single period of continuous cold. Instead, an ice age is a long interval of Earth's history during which permanent ice exists at one or both poles. Within an ice age, climate oscillates between colder periods called glacial periods and warmer periods called interglacials. Earth is currently in an ice age. Large ice sheets persist in Antarctica and Greenland. What makes today feel warm is that we are living in an interglacial period known as the Holocene, which began about 11,700 years ago. The ice age most responsible for shaping North America is known as the Late Cenozoic Ice Age, which began approximately 2.6 million years ago at the start of the Pleistocene epoch. During this time, Earth's climate repeatedly shifted between cold and warm states, driven by changes in Earth's orbit, atmospheric composition, ocean circulation, and feedbacks involving ice itself. During glacial periods, massive ice sheets expanded from polar regions into mid-latitudes. During interglacials, those ice sheets retreated, sometimes rapidly, leaving behind landscapes profoundly altered by erosion and deposition. The Pleistocene Ice Age was not one continuous freeze. Instead, it consisted of dozens of glacial cycles. Early in the Pleistocene, glacial periods occurred roughly every 40,000 years. Later, especially after about 1 million years ago, the dominant cycle shifted to roughly 100,000 years. This shift is one of the major unanswered questions in paleoclimatology and is known as the mid-Pleistocene transition. Each glacial advance did not simply repeat the previous one. Ice sheets advanced along different paths, reached different extents, and interacted with evolving landscapes left behind by earlier glaciations. North America was reshaped again and again. To understand how this happened, we must understand what causes glaciers to form and grow. Glaciers do not form simply because it is cold. They form when more snow falls in winter than melts during summer, year after year. Over time, accumulated snow compresses into firn and eventually into glacial ice. As the ice thickens, it begins to flow under its own weight. This distinction is critical. Glaciers are not static blocks of ice. They are dynamic systems that behave like very slow-moving rivers. Ice flows downhill, deforms internally, and slides over bedrock. It erodes, transports, and deposits material with extraordinary effectiveness. The growth and retreat of ice sheets are controlled by Earth's climate system, particularly by variations in solar radiation caused by changes in Earth's orbit and axial tilt. These variations are known collectively as Milankovitch cycles. Earth's orbit around the Sun is not perfectly circular. Its shape changes over time, becoming more or less elliptical. Earth's axis also tilts slightly more or less, and the timing of seasons relative to Earth's position in orbit slowly shifts. These cycles alter how much sunlight reaches different latitudes during different seasons. Crucially, glacial growth is especially sensitive to summer temperatures at high latitudes. Even if winters are extremely cold, glaciers will not grow if summers are warm enough to melt. Accumulated snow. When summer insolation decreases in northern latitudes, snow persists year-round, allowing ice sheets to expand. Once ice begins to grow, powerful feedback mechanisms amplify the process. Ice reflects sunlight far more effectively than bare ground or vegetation. As ice spreads, more solar radiation is reflected back into space, further cooling the climate. Cooler temperatures allow more ice to form, reinforcing the cycle. Atmospheric greenhouse gases also play a major role. During glacial periods, carbon dioxide concentrations are significantly lower than during interglacials. Ice core records from Antarctica show a close correlation between temperature and CO2 levels over the past 800,000 years. While the exact direction of causality is complex, greenhouse gases act as amplifiers of orbital forcing. As ice sheets expand, they begin to influence global climate patterns. They alter atmospheric circulation, shift storm tracks, and affect ocean currents. Sea level drops dramatically as water becomes locked up in ice. During the last glacial maximum, global sea level was approximately 120 meters lower than today. This drop in sea level exposed vast areas of continental shelf and created land bridges between continents. One of the most important of these was Beringia, which connected Siberia and Alaska and allowed plants, animals, and eventually humans to migrate into North America. But before we reach that stage of the story, we must focus on the ice itself. In North America, glaciation was dominated by two enormous ice sheets. The Laurentide ice sheet covered much of present-day Canada and extended deep into the United States. The Cordilleran ice sheet occupied western North America, covering parts of Alaska, British Columbia, and the Pacific Northwest. These ice sheets were not smooth domes of ice. They were complex systems with fast-flowing ice streams, stagnant zones, lobes that advanced into river valleys, and margins that fluctuated over centuries and millennia. At their maximum extent, the Laurentide ice sheet was several kilometers thick in places. Its weight depressed the Earth's crust by hundreds of meters. Even today, parts of Canada and the northern United States are still rebounding upward, a process known as isostatic rebound. This slow uplift affects modern coastlines, river gradients, and earthquake patterns. The Ice Age is not over in a geological sense. Its effects are still unfolding. As we move forward in this lecture, we will examine how these ice sheets formed, how they moved, and how they reshaped North America's surface. We will look at erosion, deposition, meltwater floods, and the creation of some of the continent's most recognizable features. But before we examine landscapes, we must first understand the character of the Pleistocene world itself. A world of shifting climates, advancing ice fronts, and ecosystems forced to adapt again and again. That world sets the stage for everything that follows. Chapter 2. The climate engine behind the ice. To understand why massive ice sheets repeatedly advanced across North America, we must examine the climate system that powered them. Glaciers do not appear randomly. Their growth and retreat are governed by predictable, measurable forces that operate on planetary scales. At the heart of the Pleistocene Ice Age lies a climate engine driven by orbital mechanics, atmospheric composition, and feedback processes that amplify small changes into continent-shaping events. We begin with Earth's orbit. Earth does not orbit the Sun in a perfectly stable way. Over tens to hundreds of thousands of years, its orbital geometry changes in regular cycles. These variations alter how solar energy is distributed across the planet, especially at high latitudes. Although the total amount of sunlight Earth receives changes very little, where and when that energy arrives changes significantly. These orbital variations are known as Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who mathematically demonstrated their climatic importance in the early 20th century. There are three primary components. The first is eccentricity. Earth's orbit shifts between being more circular and more elliptical on cycles of roughly 100,000 and 400,000 years. When the orbit is more elliptical, the difference in solar energy between perihelion and aphelion increases. This does not by itself cause ice ages, but it modulates the strength of other cycles. The second component is axial tilt, also called obliquity. Earth's axis is currently tilted about 23.5 degrees relative to its orbital plane. This tilt varies between about 22.1 and 24.5 degrees on a cycle of roughly 41,000 years. Greater tilt produces stronger seasons. Summers become warmer and winters colder, especially at high latitudes. Lower tilt weakens seasons, producing cooler summers and milder winters. For glaciation, summer temperature is far more important than winter temperature. Ice sheets grow when summer melting is insufficient to remove winter snowfall. Lower axial tilt favors ice growth by reducing summer warmth in polar and subpolar regions. The third component is precession. Earth's axis slowly wobbles like a spinning top, completing a cycle roughly every 23,000 years. Precession determines whether a hemisphere experiences summer when Earth is closer to or farther from the Sun. When northern hemisphere summers occur farther from the Sun, summer insolation decreases, favoring glacial growth. Individually, these cycles are subtle. None would freeze a continent on their own. Their power comes from their interaction with Earth's climate feedbacks. The most important of these feedbacks involves ice itself. Ice and snow reflect a large fraction of incoming sunlight. This property, known as albedo, creates a powerful cooling effect. As ice expands, more sunlight is reflected back into space. Surface temperatures drop further. Cooler temperatures allow snow to persist longer. More ice forms. The feedback reinforces itself. This is why glaciation, once initiated, can accelerate rapidly. Another critical feedback involves greenhouse gases, particularly carbon dioxide and methane. During glacial periods, atmospheric CO2 concentrations are significantly lower than during interglacials. Ice core records show that during the last glacial maximum, CO2 levels were around 180 parts per million, compared to about 280 parts per million during pre-industrial interglacials. Lower greenhouse gas concentrations reduce Earth's ability to trap heat, amplifying cooling initiated by orbital forcing. The relationship between temperature and CO2 is complex. Changes in orbit likely trigger initial cooling, which then affects ocean circulation and biological processes that remove carbon dioxide from the atmosphere. Reduced carbon dioxide further cools the planet, strengthening glaciation. Oceans play a central role in this system. The ocean is Earth's primary heat reservoir. It stores and transports enormous amounts of energy through currents such as the Atlantic meridional overturning circulation. During glacial periods, changes in freshwater input from melting ice and altered wind patterns can disrupt these currents. For example, large pulses of meltwater entering the North Atlantic reduce seawater density, slowing deep water formation. This weakens heat transport from the tropics to higher latitudes, promoting further cooling in the northern hemisphere. Sea ice also expands during glacial periods, increasing albedo and insulating the ocean from the atmosphere. This limits heat exchange and reinforces cold conditions. As ice sheets grow larger, they begin to influence climate directly. An ice sheet several kilometers thick is not just a passive feature. It alters atmospheric circulation by deflecting winds and creating persistent high-pressure systems. Storm tracks shift southward, precipitation patterns change, some regions become drier, others wetter. Ironically, larger ice sheets often experience low snowfall near their centers. Cold air holds little moisture. Ice growth is most active near the margins, where moisture from oceans can still reach the ice front. This produces lobes that advance along specific paths, shaped by topography and climate. Over time, the growing weight of ice depresses the crust beneath it. This subsidence alters regional elevation and drainage patterns. Rivers are rerouted. Basins deepen. When ice eventually retreats, the depressed land rebounds slowly upward. This process, called glacial isostatic adjustment, continues today. Parts of Hudson Bay are still rising at rates of several millimeters per year. Former shorelines tilt. Ancient beaches are stranded far above modern sea level. The climate engine driving glaciation is therefore not a simple on-off switch. It is a coupled system involving orbital forcing, atmospheric chemistry, ocean circulation, ice dynamics, and solid Earth response. This complexity explains why no two glacial cycles are identical. Early in the Pleistocene, glacial cycles followed the 41,000-year obliquity rhythm fairly closely. Ice sheets were smaller and shorter-lived. Around 1 million years ago, glacial cycles became longer and more intense, dominated by 100,000-year periods. This shift, known as the mid-Pleistocene transition, remains an active area of research. One leading hypothesis suggests that gradual cooling allowed ice sheets to grow large enough to interact more strongly with bedrock and climate feedbacks, making them more stable and harder to melt. Another possibility involves changes in atmospheric CO2 regulation or long-term tectonic influences on ocean circulation. Regardless of the exact mechanism, the result was clear. Ice sheets became massive. Glacial advances reached farther south. Their erosional and depositional power increased dramatically. North America, with its broad, relatively flat interior and proximity to moisture sources, became one of the primary theaters of glaciation on Earth. By the time of the last glacial maximum, the climate engine had driven ice to its greatest extent. Sea levels were low, atmospheric circulation was reorganized. Ecosystems were compressed into refugia at lower latitudes. In the next chapter, we will examine how ice physically moves across the landscape and how glaciers reshape the ground beneath them. Understanding glacial mechanics is essential for understanding why North America looks the way it does today. The climate engine set the conditions. Ice did the work. Chapter 3. How ice moves and shapes the land. To understand how the Ice Age reshaped North America, we must understand how ice behaves once it forms. Glaciers may appear rigid and immobile, but they are among the most effective geological agents on Earth. They erode, transport, and deposit material on continental scales, operating slowly but with immense force. Glacial ice is not static, it flows. At the most basic level, glacier movement occurs because ice is thick and heavy. Under sufficient pressure, ice behaves as a viscous solid. Individual ice crystals deform and slide past one another, allowing the entire mass to move downslope under gravity. This internal deformation is one of the primary mechanisms of glacial flow, especially in thick ice sheets. However, internal deformation alone does not explain the speed or erosive power of glaciers. A second process, basal motion, is often even more important. At the base of a glacier, pressure from overlying ice lowers the melting point of ice. Friction from movement also generates heat. As a result, a thin layer of meltwater often exists between the ice and the underlying rock. This water acts as a lubricant, allowing the glacier to slide over the bed. This basal sliding dramatically increases a glacier's ability to erode rock. Ice frozen to its bed moves slowly and causes limited erosion. Ice that slides can pluck, scrape, and grind bedrock with tremendous efficiency. Glacial erosion occurs primarily through two processes, abrasion and plucking. Abrasion happens when rock fragments embedded in the base of the glacier scrape against the bedrock. These fragments act like sandpaper, grinding and polishing the surface beneath. Over time, abrasion smooths bedrock, producing striations that record the direction of ice movement. These striations, often preserved on exposed bedrock, are among the most direct pieces of evidence for past glaciation. They allow geologists to reconstruct ice flow directions thousands of years after the ice has vanished. Plucking occurs when meltwater seeps into cracks in the bedrock beneath the glacier. As temperatures fluctuate, the water refreezes, expanding and loosening blocks of rock. When the glacier moves forward, it pulls these blocks free and incorporates them into the ice. Plucking is particularly effective in areas with jointed or fractured bedrock. It produces steep, jagged landscapes and is responsible for many of the sharp cliffs and over-deepened basins found in formerly glaciated regions. Together, abrasion and plucking allow glaciers to reshape entire landscapes. Valleys are widened and deepened. Mountains are truncated. Drainage divides are breached. One of the most distinctive results of glacial erosion is the transformation of river valleys into U-shaped valleys. Before glaciation, rivers carve five-shaped valleys with narrow bottoms and sloping sides. When glaciers occupy these valleys, they erode both the floor and the walls, producing broad flat bottoms and steep sides. Although this effect is most dramatic in mountainous regions, similar processes occurred beneath continental ice sheets. Subglacial valleys were carved into bedrock, some of which later became lakes or were buried beneath sediment. Glaciers are not only erosional agents, they are also powerful transport systems. As glaciers move, they carry enormous amounts of debris. This material includes fine rock flour, sand, gravel, and massive boulders. Some of it is eroded locally. Some is transported hundreds or even thousands of kilometers from its source. Material carried by glaciers is known collectively as till when it is deposited directly by ice. Till is typically unsorted and unstratified. Fine particles and large clasts are mixed together with no layering. This chaotic texture reflects the direct release of debris from melting ice. When ice melts, it deposits this load across the landscape, forming a wide variety of landforms. Moraines are among the most important of these. A moraine is a ridge or mound of till deposited at the edge of a glacier or ice sheet. Terminal moraines mark the maximum extent of glacial advance. Recessional moraines form during pauses or minor re-advances as ice retreats. In North America, many major cities sit near ancient moraines. These features often form natural ridges, influence drainage patterns and control soil distribution. Lateral moraines form along the sides of valley glaciers, while medial moraines form when two glaciers merge and their debris bands combine. Under continental ice sheets, moraines can be more subtle but still define former ice margins. Another important depositional feature is the drumlin. Drumlins are elongated hills composed of till, streamlined in the direction of ice flow. They are typically hundreds of meters long and tens of meters high. Drumlins form beneath actively flowing ice and record the direction and dynamics of ice movement. Large drumlin fields indicate fast-flowing ice streams beneath ice sheets. These ice streams drained ice from the interior toward the margins and played a critical role in ice sheet stability. The exact mechanism of drumlin formation is still debated, but it likely involves deformation of subglacial sediments under high pressure and shear stress. Not all glacial deposits are made directly by ice. Meltwater plays a major role in redistributing sediment. As glaciers melt, they release vast quantities of water that flow beneath, within, and beyond the ice. Sediment deposited by meltwater is known as outwash. Unlike till, outwash is sorted and stratified. Flowing water separates particles by size, producing layers of sand and gravel. Outwash plains form beyond glacier margins, often extending tens of kilometers. These plains are typically flat and well drained. Many modern agricultural regions owe their soils and topography to outwash deposition. Subglacial meltwater can carve tunnels beneath the ice. When these tunnels collapse or fill with sediment, they form sinuous ridges called eskers. Eskers trace the paths of ancient meltwater rivers that once flowed beneath kilometers of ice. Because eskers are elevated and well drained, they were often used by indigenous peoples and later by settlers as natural travel corridors. Another important meltwater feature is the Kettle Lake. Kettle lakes form when blocks of stagnant ice become buried in outwash sediment. When the ice eventually melts, it leaves behind a depression that fills with water. These lakes are common in formerly glaciated regions and often have no surface inlets or outlets. The combined effect of erosion, transport, and deposition by ice is landscape reorganization on a massive scale. Rivers are diverted or dammed by ice. Lakes form where none existed before. Drainage networks are reorganized. Entire regions acquire new topographic identities. Importantly, glacial processes are not uniform across an ice sheet. Ice thickness, velocity, temperature, and substrate vary spatially. As a result, glaciation produces a patchwork of landforms that record different processes operating simultaneously. Understanding how ice moves and shapes land provides the foundation for understanding specific regions of North America. In the next chapter, we will turn our attention to the largest ice mass of all, the Laurentide ice sheet, and examine how it developed, expanded, and came to dominate the continent. Chapter 4. The Laurentide ice sheet. The Laurentide ice sheet was the dominant force behind North America's glacial transformation. At its maximum extent, it was one of the largest ice masses to exist on Earth outside of Antarctica. Understanding its structure, growth, and behavior is essential to understanding the ice age that shaped the continent. The Laurentide ice sheet formed over northern North America during the Pleistocene epoch. Its core regions lay over what is now central and eastern Canada, including the Canadian Shield. This region provided ideal conditions for ice sheet development. High latitude, relatively low relief, and hard crystalline bedrock allowed snow to accumulate and persist over long periods. As snowfall exceeded summer melting, ice thickened and spread outward from multiple centers of accumulation. These centers eventually coalesced into a single massive ice sheet covering millions of square kilometers. At its peak during the last glacial maximum, approximately 20,000 years ago, the Laurentide ice sheet extended from the Arctic Ocean southward into the present-day United States. It covered all of present-day Canada east of the Rocky Mountains and large portions of the northern United States. Ice reached as far south as present-day New York, Pennsylvania, Ohio, Indiana, Illinois, Missouri, and parts of the Great Plains. In the northeast, it extended into New England and reshaped the Atlantic coastline. In places, the ice sheet was more than 3 kilometers thick. This immense thickness created pressures high enough to deform bedrock and significantly depress the crust beneath it. The Laurentide ice sheet was not a uniform slab of ice. It was a dynamic, structured system composed of multiple domes, saddles, and fast-flowing ice streams. Major domes formed over regions such as the Keewatin region of central Canada, the Labrador region, and the Fox Basin. From these domes, ice flowed outward in all directions, guided by underlying topography and influenced by climate patterns. Ice flow was not slow everywhere. Beneath parts of the ice sheet, narrow corridors of fast-moving ice developed. These ice streams transported large volumes of ice from the interior toward the margins. They played a crucial role in controlling the overall stability and behavior of the ice sheet. Evidence for these ice streams is preserved in the landscape in the form of streamlined landforms, such as drumlins and megascale glacial lineations. These features indicate sustained, directional ice movement over long distances. The Laurentide ice sheet exerted enormous influence on Earth's climate system. Its sheer size affected atmospheric circulation across the northern hemisphere. The ice surface created a cold, high-elevation plateau that deflected winds and altered storm tracks. Westerly winds were forced southward, changing precipitation patterns across North America. Regions south of the ice margin experienced cooler, drier conditions. Deserts expanded in parts of the interior west. At the same time, Increased precipitation fell along the ice margin, feeding glacial growth and meltwater systems. The presence of the ice sheet also contributed to global sea level lowering. As water became locked in ice, sea level dropped by more than 100 meters. This exposed continental shelves and altered coastlines worldwide. One of the most important consequences of Laurentide growth was the development of preglacial lakes. As the ice advanced and retreated, it repeatedly blocked natural drainage pathways. Meltwater became trapped between the ice margin and higher ground, forming enormous lakes. Some of these lakes were larger than any modern freshwater body. Among the most famous was Lake Agassiz, which formed along the southern margin of the Laurentide ice sheet. At its largest, Lake Agassiz covered portions of present-day Manitoba, Ontario, Minnesota, North Dakota, and beyond. Lake Agassiz did not exist as a single stable lake. Its size and shape changed as ice margins shifted and drainage outlets opened or closed. When outlets failed, catastrophic floods occurred, releasing massive volumes of freshwater into the oceans. These outburst floods had global consequences. Freshwater pulses into the North Atlantic disrupted ocean circulation and may have contributed to abrupt climate events such as the Younger Dryas, a sudden return to near glacial conditions during deglaciation. The Laurentide ice sheet also profoundly altered North America's drainage systems. Many modern rivers owe their courses to glacial interference. The Ohio River, for example, formed when ice blocked northward flowing rivers, forcing water to find new pathways along the ice margin. Similarly, parts of the Missouri and Mississippi systems were reorganized by glacial advances. In the Great Lakes region, repeated glaciation carved deep basins into bedrock and deposited moraines that acted as natural dams. When the ice retreated, meltwater filled these basins, forming the ancestral Great Lakes. The current configuration of the Great Lakes is a product of the final stages of Laurentide retreat. Earlier, lake stages had different outlets and water levels, reflecting ongoing isostatic rebound and changing drainage routes. Isostatic effects extended far beyond the ice margin. As the Laurentide ice sheet grew, it depressed the crust beneath it by hundreds of meters. Surrounding regions experienced forebulge uplift, where the crust flexed upward in response to ice loading. This uplift affected regions south of the ice margin. When the ice melted, the depressed crust began to rebound, while the forebulge collapsed. This process altered relative sea levels along coastlines and continues to influence regional geology today. In eastern Canada and parts of the northeastern United States, former shorelines now lie well above present sea level. In contrast, regions that were once part of the forebulge may now be subsiding. The Laurentide ice sheet did not simply appear and disappear once. It advanced and retreated multiple times over the Pleistocene. Each advance reshaped landscapes already modified by earlier glaciations. Each retreat left behind new deposits and drainage patterns. By the time of the last glacial maximum, North America had been transformed repeatedly by ice. The final retreat would set the stage for modern ecosystems, human migration, and the landscapes we recognize today. In the next chapter, we will turn our attention to the Cordilleran ice sheet and the western margin of North America, where ice interacted with mountains, coastlines, and volcanic terrain in ways very different from the Laurentide experience. Chapter 5. The Cordilleran ice sheet and the western margin. While the Laurentide ice sheet dominated central and eastern North America, a very different glacial system developed along the western edge of the continent. This system, known as the Cordilleran ice sheet, covered much of present-day Alaska, British Columbia, and parts of the Pacific Northwest. Although smaller than the Laurentide, the Cordilleran ice sheet played a critical role in shaping western North America and interacted with the landscape in fundamentally different ways. The Cordilleran ice sheet formed in a region of complex topography. Unlike the broad, relatively flat Canadian shield beneath the Laurentide ice sheet, the Cordilleran region is defined by mountain ranges, deep valleys, volcanic plateaus, and an irregular coastline. These features strongly influenced how ice accumulated, flowed, and retreated. Ice initially formed in high-elevation mountain ranges such as the Coast Mountains, the Columbia Mountains, and the St. Elias Mountains. Valley glaciers expanded downslope, merging with neighboring glaciers. Over time, these coalesced into an interconnected ice mass that buried much of the mountainous terrain beneath a continuous ice cover. At its maximum extent, the Cordilleran ice sheet covered nearly all of British Columbia and extended into southern Alaska, the Yukon, northern Washington, northern Idaho, and western Montana. In many regions, only the highest mountain peaks protruded above the ice surface, forming isolated nunataks. Ice thickness in the Cordilleran ice sheet commonly exceeded 1 to 2 kilometers in interior regions. As with the Laurentide, this immense weight depressed the crust and altered regional topography. However, because of the rugged terrain beneath it, the Cordilleran ice sheet behaved very differently from its eastern counterpart. Ice flow was strongly controlled by valleys and mountain corridors. Instead of radiating outward from broad domes, ice was funneled through low-elevation pathways toward the coast and interior basins. This produced fast-flowing outlet glaciers that carved deep troughs into bedrock. Many of the fjords along the coast of British Columbia and Alaska owe their existence to these outlet glaciers. Ice-carved valleys well below present sea level. When the ice retreated and sea level rose, seawater flooded these troughs, creating the steep-sided, deep fjords seen today. The Cordilleran ice sheet was also strongly influenced by maritime climate conditions. Proximity to the Pacific Ocean meant that moisture was abundant. Heavy snowfall fed rapid ice growth, especially along the western margins. At the same time, relatively mild temperatures near the coast promoted melting and dynamic ice margins. This combination produced highly active glaciers with strong erosive power. One of the most significant interactions between the Cordilleran ice sheet and the Laurentide ice sheet occurred in western Canada. At several points during the Pleistocene, the two ice sheets advanced toward one another. When they met, they formed a continuous ice barrier stretching from the Pacific Ocean to the Atlantic. This barrier blocked north-south drainage across the continent. The presence or absence of an ice-free corridor between the two ice sheets has major implications for human migration into the Americas. For much of the last glacial maximum, the corridor was likely closed or environmentally hostile. Only later, as ice retreated, did a viable corridor open. Alternatively, some evidence suggests that early human populations may have traveled along the Pacific coast, using ice-free refugia and marine resources. The retreat patterns of the Cordilleran ice sheet are therefore closely tied to questions of human settlement. The Cordilleran ice sheet also produced enormous volumes of meltwater. As ice retreated, meltwater flowed through valleys and across plateaus, carving channels and depositing sediment. In some cases, meltwater was temporarily dammed by ice or moraines, forming large proglacial lakes. One of the most dramatic examples of glacial flooding in North America occurred at the southern margin of the Cordilleran ice sheet in what is now eastern Washington. Here, a lobe of the Cordilleran ice sheet blocked the Clark Fork River, creating glacial Lake Missoula. This lake grew to enormous size, holding more water than Lake Erie and Lake Ontario combined. When the ice dam failed, water was released catastrophically. Floodwaters swept across eastern Washington at tremendous speed, scouring bedrock, stripping soils, and creating a landscape of coulees, cataracts, and giant ripple marks. These events, known collectively as the Missoula floods, occurred multiple times over several thousand years. They reshaped the Columbia Plateau and provide some of the clearest evidence for catastrophic meltwater processes during deglaciation. The Cordilleran ice sheet also influenced volcanic landscapes. In regions such as the Cascade Range, glaciers interacted with active and dormant volcanoes. Ice confined lava flows, altered eruption styles, and preserved volcanic features beneath ice. Some volcanoes show clear evidence of having erupted beneath or alongside glaciers. This interaction between ice and volcanism produced distinctive landforms, including flat-topped volcanoes formed by eruptions beneath ice. As the Cordilleran ice sheet retreated, it did not melt uniformly. Lower elevation valleys became ice-free first, while high elevation ice persisted longer. This produced complex patterns of meltwater routing and sediment deposition. Many modern river systems in the Pacific Northwest reflect these glacial legacies. Isostatic rebound followed deglaciation in the West as well, though its expression differs from that in eastern North America due to variations in crustal structure and ice thickness. Coastal regions experienced relative sea level changes as land rebounded and global sea level rose. Some areas show evidence of rapid shoreline shifts during the early Holocene. The Cordilleran ice sheet, though smaller than the Laurentide, left an outsized imprint on western North America. It carved fjords, reshaped river systems, produced catastrophic floods, and influenced the pathways of human migration. Together, the Laurentide and Cordilleran ice sheets transformed the continent from coast to coast. In the next chapter, we will examine how these ice sheets shaped some of North America's most iconic features, including the Great Lakes, major river systems, and vast interior plains. Chapter 6. Ice, Water, and the Making of North America's Landscapes. By the time the Laurentide and Cordilleran ice sheets reached their maximum extents, ice had already done immense work. But much of North America's most recognizable geography was shaped not only by ice itself, but by the water released as that ice advanced, stagnated, and retreated. Glacial meltwater was one of the most powerful agents of landscape change during the Ice Age. It carved valleys, reorganized drainage systems, deposited thick sediment layers, and created many of the continent's largest lakes and plains. In many regions, meltwater effects rivaled or exceeded direct glacial erosion. Nowhere is this more evident than in the Great Lakes region. The basins that hold the modern Great Lakes existed before the Ice Age, but they were dramatically deepened and reshaped by repeated glaciation. The Laurentide ice sheet advanced over this region multiple times, exploiting zones of weaker bedrock and widening existing valleys. Differential erosion played a key role. Softer sedimentary rocks were eroded more easily than harder crystalline rocks, producing uneven basins. Glacial abrasion and plucking deepened these basins, while moraines deposited at their margins acted as natural dams. As the ice retreated, meltwater filled the depressions, forming a series of ancestral lakes that evolved through multiple stages. Each stage had different outlets, water levels, and shorelines as ice margins shifted and the crust rebounded. For example, early proglacial lakes drained southward through river systems that no longer exist today. As northern outlets opened following ice retreat, drainage shifted toward the St. Lawrence River system. Isostatic rebound continues to tilt lake basins even now, subtly altering shorelines and water levels. The Great Lakes are therefore not static features. They are dynamic systems still responding to the end of glaciation. Meltwater also played a crucial role in shaping North America's major river systems. Before glaciation, many rivers in the northern United States flowed northward into what is now Canada. Advancing ice blocked these routes, forcing rivers to find new paths along the ice margin. The Ohio River is a prime example. It did not exist as a major river before the Ice Age. Instead, it formed when ice blocked north-flowing rivers, causing water to pond and eventually overflow southward. This new drainage route became entrenched and persists today. Similarly, portions of the Missouri and Mississippi river systems were reorganized by glacial activity. Meltwater from the ice sheets fed enormous braided rivers that carried vast sediment loads southward. These rivers deposited thick alluvial sediments across the interior plains. The result was the formation of broad flat landscapes such as the central lowlands and the interior plains. Much of the fertile agricultural land in the Midwest exists because glacial processes created deep, nutrient-rich soils derived from glacial till and less. Less is a fine-grained, wind-blown sediment composed primarily of silt. During glacial periods, large amounts of fine sediment were produced by glacial grinding. Meltwater rivers spread this sediment across floodplains, where it dried and was carried by wind. Over time, thick loess deposits accumulated downwind of glaciated regions, especially along the Mississippi Valley. These deposits now support some of the most productive farmland on Earth. Meltwater did not always flow gently. In many cases, meltwater was released catastrophically. Ice dams failed. Proglacial lakes drained suddenly. Floodwaters surged across the landscape with extraordinary force. The Missoula floods of the Pacific Northwest are the most famous example, but they were not unique. Similar outburst floods occurred elsewhere, including from Lake Agassiz along the Laurentide ice sheet margin. When Lake Agassiz drained, meltwater was released into the North Atlantic through various outlets over time. These freshwater pulses disrupted ocean circulation and likely contributed to abrupt climate shifts. On land, these floods carved channels, scoured bedrock, and deposited large gravel bars. Evidence of such floods can still be seen in oversized river valleys and abandoned channels far larger than modern rivers could produce. Meltwater also created thousands of smaller lakes across formerly glaciated regions. Kettle lakes formed where blocks of stagnant ice melted. Moraine-dammed lakes formed behind ridges of till. In some cases, ice scoured depressions that later filled with water. These lakes influence local climate, ecosystems, and human settlement patterns. In regions like Minnesota, Wisconsin, and Ontario, glacial lakes are a defining feature of the landscape. Along the coasts, meltwater and isostatic rebound interacted with rising sea levels in complex ways. As ice melted, global sea level rose due to the return of water to the oceans. At the same time, land previously depressed by ice began to rebound upward. The balance between these processes determined relative sea level change at any given location. In some regions, land rose faster than sea level, leaving former shorelines stranded inland. In others, sea level rise outpaced rebound, drowning coastal landscapes and creating estuaries. The modern coastline of North America reflects this interplay. Features such as drowned river valleys, barrier islands, and raised beaches all record the legacy of glacial meltwater and crustal adjustment. Taken together, ice and water worked as a coupled system. Ice sculpted the land directly, while meltwater amplified and redistributed its effects. Landscapes were not shaped once, but repeatedly, as ice advanced and retreated across the continent. By the end of the last glacial maximum, North America had been transformed into a mosaic of basins, plains, rivers, and lakes. The stage was set for one of the most rapid environmental transitions in Earth's recent history. In the next chapter, we will examine how the Ice Age came to an end, how rapidly ice retreated, and how climate shifted into the warmer interglacial world we now inhabit. Chapter 7. Deglaciation and the end of the Ice Age. The end of the last glacial period was not a simple, gradual warming. It was a complex, uneven transition marked by rapid climate shifts, collapsing ice margins, massive meltwater pulses, and landscapes changing on timescales meaningful even to human lifetimes. This process, known as deglaciation, began roughly 20,000 years ago and reshaped North America as profoundly as the ice advances that came before it. Deglaciation was initiated by changes in Earth's orbital configuration. Northern Hemisphere summer insolation began to increase due to shifts in axial tilt and precession. Summers became warmer, especially at high latitudes. This increased summer melting reduced the net mass balance of ice sheets. Once summer melt began to exceed winter snowfall, ice sheets entered a phase of retreat. Importantly, retreat did not occur because the ice flowed backward. Ice always flows outward from its center of mass. Retreat happens when melting at the margins outpaces forward flow. The ice margin migrates inward even as ice continues to move toward it. This distinction helps explain why deglaciation can be both rapid and chaotic. As the Laurentide ice sheet began to retreat, its margins became highly unstable. Meltwater pooled on the ice surface and at its base. Crevasses widened. Ice shelves and lobes thinned and collapsed. In many regions, retreat occurred in pulses rather than smoothly. Periods of relatively stable ice margins were punctuated by rapid retreats spanning tens or even hundreds of kilometers. One of the most striking features of deglaciation is the speed at which it occurred. Geological evidence indicates that large portions of the Laurentide ice sheet disappeared within a few thousand years. In some regions, ice retreated at rates exceeding several hundred meters per year. This is fast by geological standards and had enormous environmental consequences. As ice retreated, meltwater production increased dramatically. Rivers swollen with glacial meltwater carved new channels and reoccupied old ones. Proglacial lakes expanded and drained repeatedly. Sediment loads increased, reshaping floodplains and deltas. The retreating ice exposed vast areas of freshly eroded ground. These surfaces were initially barren, composed of till, gravel, and bedrock. Over time, soils began to form as physical weathering, chemical processes, and biological activity took hold. Vegetation followed the retreating ice northward. Pollen records preserved in lake sediments provide detailed records of postglacial ecological succession. Initially, tundra species dominated newly exposed landscapes. Grasses, sedges, and low shrubs colonized first. As climate warmed, boreal forests advanced northward. Eventually, temperate forests expanded into regions that had been ice-covered only a few thousand years earlier. This migration of ecosystems did not occur uniformly. Topography, soil development, and moisture availability influenced local patterns. In some areas, cold-tolerant species persisted longer. In others, warmer conditions arrived quickly. Deglaciation also had major impacts on global climate. One of the most significant events during this transition was the Younger Dryas, a sudden return to near glacial conditions that occurred approximately 12,900 years ago. During the Younger Dryas, temperatures in the northern hemisphere dropped sharply within decades. Glaciers temporarily stabilized or even advanced. Vegetation zones shifted southward. The leading hypothesis for this event involves meltwater from proglacial lakes, particularly Lake Agassiz, entering the North Atlantic. The influx of fresh water reduced seawater density and disrupted thermohaline circulation. This weakened heat transport to the north, triggering rapid cooling despite increasing solar insolation. The Younger Dryas illustrates a key lesson of deglaciation. Earth's climate system can respond abruptly to relatively small perturbations, especially when large ice sheets and ocean circulation are involved. Eventually, however, warming resumed. By approximately 11,700 years ago, the climate entered the Holocene interglacial. The Holocene is characterized by relatively stable temperatures compared to the Pleistocene. Ice sheets retreated to their modern extents. Sea levels rose to near present-day levels. This stability allowed ecosystems to mature and human societies to develop agriculture, permanent settlements, and complex civilizations. But even during the Holocene, the legacy of deglaciation continued to shape North America. Isostatic rebound accelerated as ice loads disappeared. Rivers adjusted their gradients. Coastlines shifted. In some regions, earthquakes occurred as the crust responded to unloading. Deglaciation also released enormous amounts of fresh water and nutrients into lakes and oceans. These inputs influenced aquatic ecosystems and biogeochemical cycles. From a geological perspective, deglaciation represents a phase of intense reorganization. Landscapes adjusted from ice-dominated systems to fluvial and ecological ones. Drainage networks stabilized, soils deepened, forests spread. For humans, this transition was transformative. As ice retreated, new land became available for habitation. Migration routes opened, resources expanded. The timing and pathways of human settlement in North America are closely linked to the pattern of ice retreat and environmental change. The end of the Ice Age was not an ending in the sense of finality. It was a transition. One regime of Earth system behavior gave way to another. Understanding deglaciation is critical because it demonstrates how quickly large-scale environmental change can occur once key thresholds are crossed. In the next chapter, we will examine how humans encountered and interacted with the Ice Age landscape and how glaciation influenced the peopling of North America. Chapter 8. Ice Age North America and the First Humans. The arrival of humans in North America occurred against the backdrop of a continent still deeply shaped by ice. Glaciers controlled migration routes, determined where plants and animals could live, and governed the availability of fresh water and resources. Understanding the Ice Age landscape is therefore essential to understanding how and when humans entered and spread across North America. For much of the 20th century, the dominant explanation for human migration into the Americas focused on a single route. This route was the Bering Land Bridge, known as Beringia, and an interior ice-free corridor that opened between the Laurentide and Cordilleran ice sheets. Beringia formed when global sea levels dropped during glacial periods. With sea level more than 100 meters lower than today, the shallow continental shelf between Siberia and Alaska was exposed. This created a vast landmass connecting Asia and North America. Beringia was not a narrow land bridge. At its maximum extent, it was hundreds of kilometers wide. It supported a cold but productive ecosystem dominated by grasses, herbs, and shrubs. This environment, sometimes called the Mammoth Steppe, supported large herbivores such as mammoths, bison, horses, and musk oxen. These animals provided a strong incentive for human populations to move eastward. Genetic and archaeological evidence suggests that human groups entered Beringia from Northeast Asia sometime before 20,000 years ago. However, ice sheets blocked further movement into the interior of North America for thousands of years. During the last glacial maximum, the Laurentide and Cordilleran ice sheets merged, forming a continuous barrier across much of the continent. Southward movement was not possible through the interior. This led to the concept of a Beringian standstill. Human populations may have lived in Beringia for several thousand years, isolated from both Asia and the rest of North America, adapting to cold conditions and developing distinct genetic lineages. Eventually, as deglaciation progressed, pathways into the continent opened. One possible route was the interior ice-free corridor. This corridor formed as the Laurentide and Cordilleran ice sheets retreated from one another, creating a north-south passage through western Canada. However, recent evidence suggests that even when the corridor became physically open, it may not have been ecologically viable. Early on, the corridor lacked sufficient plant and animal life to support human travel and settlement. Glacial landscapes are often initially barren, with thin soils and limited resources. An alternative route is the coastal migration hypothesis. Along the Pacific coast, retreating ice may have left ice-free refugia earlier than the interior corridor. Sea levels were lower, exposing coastal plains and islands. Marine resources such as fish, shellfish, and marine mammals could have supported human populations traveling southward by boat or along shorelines. The Cordilleran ice sheet played a critical role in shaping this coastal environment. Its retreat opened pathways along the coast while still blocking the interior. Unfortunately, much of the archaeological evidence for early coastal migration is now submerged due to post-glacial sea level rise. This makes direct confirmation difficult, but growing evidence supports the plausibility of this route. By at least 15,000 years ago, humans were present south of the ice sheets. Sites such as Monteverde in Chile indicate that people reached the southern tip of South America remarkably quickly once entry was possible. This rapid dispersal suggests that migration routes were open and that populations were highly adaptable. The Ice Age landscape influenced not only where humans could travel, but how they lived. Glacial environments produced highly variable ecosystems. Large herbivores migrated seasonally in response to vegetation and climate. Human groups likely followed these animals, developing flexible subsistence strategies. Water availability was also critical. Meltwater rivers, proglacial lakes, and newly formed wetlands provided fresh water and attracted animals. Many early archaeological sites are located near former glacial lakes or meltwater channels. Glaciation also shaped raw material availability. Glaciers transported and deposited stone from distant sources. Glacial till and outwash provided access to high-quality lithic materials such as chert, obsidian, and quartzite. These materials were used to manufacture tools and weapons. In some regions, distinctive stone types transported by glaciers allow archaeologists to trace human movement and trade networks across large distances. As climate warmed during deglaciation, human populations adapted to rapidly changing conditions. Megafaunal extinctions occurred near the end of the Pleistocene. Many large mammals that thrived in Ice Age ecosystems disappeared, including mammoths, mastodons, and giant ground sloths. The causes of these extinctions remain debated. Climate change altered habitats. Human hunting may have contributed. It is likely that multiple factors acted together during a period of rapid environmental change. As megafauna declined, human groups diversified their subsistence strategies. Hunting smaller animals, fishing, and plant gathering became increasingly important. These changes set the stage for regional cultural differentiation. By the early Holocene, North America was no longer an ice-dominated continent. Forests expanded, grasslands shifted, coastlines stabilized. Human societies responded to these changes by settling new regions, developing localized technologies, and forming long-term relationships with their environments. The Ice Age did not merely provide a backdrop for human history, it actively structured the possibilities for migration, survival, and adaptation. In the next chapter, we will examine the lasting geological legacy of the Ice Age in the modern landscape, and explore how glacial processes continue to influence North America today. Chapter 9. The Ice Age Legacy in the Modern Landscape. Although the great continental ice sheets vanished thousands of years ago, their influence is everywhere. Much of modern North America is best understood as a post-glacial landscape, still adjusting to the disappearance of ice that once dominated the continent. Rivers, soils, coastlines, ecosystems, and even patterns of human settlement reflect decisions made not by people, but by ice. One of the most pervasive legacies of the Ice Age is topography. Large portions of northern North America exhibit a subdued, rolling landscape characterized by gentle hills, shallow depressions, and poorly integrated drainage. This terrain contrasts sharply with the deeply incised river valleys and rugged relief of unglaciated regions. These differences are not accidental. Glacial erosion stripped away pre-existing weathered surfaces and irregularities, while glacial deposition smoothed the landscape with thick blankets of till and outwash. The result is a landscape that appears young in geological terms. In regions formerly covered by the Laurentide ice sheet, bedrock is often buried beneath tens of meters of glacial sediment. This sediment masks structural features and controls surface hydrology. Streams may be poorly organized, lakes are abundant, and wetlands are widespread. The prevalence of lakes in regions such as Minnesota, Wisconsin, Ontario, and Quebec is a direct result of glaciation. Depressions created by ice scour, kettle formation, and moraine damming filled with water as ice retreated. Many of these lakes have no surface outlets and are sustained by groundwater and precipitation. Drainage networks in glaciated regions often appear immature. Rivers may follow indirect paths, shift course frequently, or terminate in lakes. This reflects the relatively short time since deglaciation. From a geological perspective, 11,000 years is barely enough time for rivers to fully reorganize a landscape. Soils represent another critical glacial legacy. Much of North America's most productive agricultural land lies within formerly glaciated regions. Glacial till and less provide mineral-rich parent material that weathers into fertile soils. These soils retain moisture well and support intensive agriculture. In contrast, unglaciated regions often have older, more weathered soils that are thinner and less nutrient-rich. The distribution of agriculture across North America closely mirrors the southern limits of Pleistocene glaciation. Groundwater systems are also shaped by glacial deposits. Outwash sands and gravels form highly permeable aquifers capable of storing and transmitting large volumes of water. Many cities and rural communities rely on groundwater resources hosted in glacial sediments. At the same time, layers of compacted till can act as aquittards, restricting groundwater flow and creating complex subsurface hydrology. Understanding these glacial deposits is essential for water resource management, contamination studies, and infrastructure planning. The Ice Age also left a strong imprint on modern river behavior. Many rivers inherited oversized valleys carved by glacial meltwater. Today's rivers often appear too small to have created the valleys they occupy. This mismatch is a hallmark of post-glacial landscapes. Examples include the upper Mississippi River and many tributaries across the Midwest. During deglaciation, these rivers carried immense volumes of meltwater. As ice disappeared and discharge declined, rivers adjusted to smaller flows but remained confined within large valleys. Isostatic rebound continues to influence modern geology. As land previously depressed by ice rebounds upward, river gradients change. Some rivers are actively incising, while others are adjusting their courses. In coastal regions, uplift alters relative sea level, affecting estuaries and shoreline stability. In parts of eastern Canada, rebound rates remain high enough to produce measurable seismic activity. Earthquakes in these regions are often linked to crustal stress adjustments following deglaciation. The Ice Age also influenced mineral and resource distribution. Glacial transport concentrated economically important materials in certain areas. Sand and gravel resources derived from glacial deposits are widely used in construction. Placer deposits formed from glacial reworking of sediments concentrate heavy minerals. In some regions, glacial processes exposed bedrock resources that might otherwise remain buried. In others, thick sediment cover complicates exploration. Ecosystems reflect glacial history as well. The distribution of plant and animal species across North America bears the imprint of Ice Age refugia and migration pathways. Forest types, species diversity, and genetic patterns all reflect post-glacial recolonization from southern refuges. Some species have disjunct distributions because populations became isolated during glaciation and never fully reconnected. Others expanded rapidly as climate warmed, filling newly available habitats. Even modern climate patterns are influenced by glacial legacies. Large lakes moderate regional temperatures, reduce seasonal extremes, and generate lake-effect precipitation. The Great Lakes, for example, influence weather patterns across much of the eastern United States and Canada. Surface albedo, soil moisture, and vegetation patterns inherited from glaciation continue to affect regional climate interactions. Human infrastructure has adapted to these glacial landscapes. Transportation corridors often follow glacial valleys and outwash plains. Cities develop near lakes, rivers, and fertile soils created by glacial processes. Boundaries between states and provinces sometimes reflect glacial landforms and drainage divides. Understanding glacial geology is therefore not an academic exercise. It informs land use planning, water management, hazard assessment, and environmental conservation. The Ice Age did not simply shape a prehistoric world, it built the foundation upon which modern North America exists. In the final chapter, we will step back and place the Ice Age into a longer perspective, examining what it tells us about Earth's climate system, future glaciations, and the long-term forces that continue to shape the continent. Chapter 10. What the Ice Age tells us about Earth's past and future. The Ice Age that shaped North America is not merely a chapter of ancient history. It is a case study in how Earth's climate system operates, how landscapes respond to large-scale forcing, and how quickly profound environmental change can occur once critical thresholds are crossed. From a geological perspective, the Pleistocene Ice Age demonstrates that Earth's climate is not static. It oscillates between states, sometimes gradually, sometimes abruptly. Small changes in solar energy distribution, driven by orbital mechanics, can initiate feedbacks powerful enough to cover continents in ice. This sensitivity is one of the most important lessons of the Ice Age. Orbital forcing alone does not create kilometer-thick ice sheets. It merely nudges the system. Ice growth accelerates because of feedbacks involving albedo, greenhouse gases, ocean circulation, and ice dynamics. Once these feedbacks engage, climate change becomes self-reinforcing. The reverse is also true. Once ice sheets begin to collapse, warming can accelerate rapidly. Deglaciation illustrates that climate transitions do not always occur smoothly. The Younger Dryas shows that large-scale cooling can occur within decades when freshwater input disrupts ocean circulation. This challenges the assumption that climate change is always slow and predictable. The Ice Age also reveals how tightly coupled Earth systems are. Ice sheets interact with the atmosphere by altering wind patterns and precipitation. They interact with oceans by changing freshwater flux and sea level. They interact with the solid Earth by depressing and rebounding the crust. No component operates in isolation. This coupling is why glaciation reshaped North America so thoroughly. Ice did not merely erode mountains and deposit sediment. It reorganized drainage networks, restructured ecosystems, and influenced where humans could live. From a long-term perspective, ice ages are not unusual. Earth has experienced multiple ice ages throughout its history. The late Cenozoic Ice Age is only the most recent. Earlier ice ages occurred during the Paleozoic and even in the Precambrian, when ice may have reached equatorial latitudes. What distinguishes the Pleistocene Ice Age is not its existence, but its timing. It coincided with the evolution of modern humans and the development of complex ecosystems similar to those we recognize today. This coincidence allows us to study Ice Age processes in extraordinary detail using geological evidence, ice cores, fossils, and archaeological records. It also raises an important question. Are we still in an Ice Age? From a geological standpoint, the answer is yes. Permanent ice still exists at the poles. The Holocene is an interglacial period within a longer ice age. If past patterns hold, Earth would eventually return to a glacial state as orbital conditions shift. However, this natural trajectory is now complicated by human activity. Atmospheric carbon dioxide concentrations today are far higher than at any point during the Pleistocene. These elevated greenhouse gas levels alter Earth's energy balance in ways that orbital forcing alone cannot counteract in the near term. Current research suggests that future glaciations may be delayed or suppressed for tens of thousands of years due to anthropogenic warming. The climate system has been pushed into a new regime. This does not mean that ice sheets are irrelevant. Greenland and Antarctic ice remain sensitive to warming. Their loss would raise sea levels dramatically and reshape coastlines worldwide. The Ice Age provides context for understanding these changes. It shows how ice responds to climate forcing, how meltwater influences ocean circulation, and how landscapes respond to changing base levels. It reminds us that ice is not merely a passive indicator of climate. It is an active agent that can amplify change. The legacy of the Ice Age is written across North America. Every lake basin, moraine ridge, fertile plain, and misfit river valley tells part of the story. Even regions never directly covered by ice were shaped by its presence through altered climate, sediment delivery, and hydrology. From the Great Lakes to the Columbia Plateau, from New England's rocky coast to the less plains of the Midwest, ice determined form and function. Perhaps the most important insight the Ice Age offers is perspective. Human timescales are short, geological timescales are vast, yet the Ice Age bridges these scales. Its end occurred recently enough that its effects remain visible, measurable, and ongoing. Rivers are still adjusting. Crust is still rebounding. Ecosystems still reflect post-glacial histories. The Ice Age is not over in the sense that its work is complete. Understanding this history allows us to read the landscape more clearly. It allows us to recognize that the ground beneath our feet is the product of slow but relentless processes operating over immense spans of time. Ice reshaped North America, not through violence, but through persistence. And in that persistence lies one of the most powerful lessons geology has to offer.